Today we're going to try to figure out how to get an empirical formula of a hydrocarbon. This would be CH, CHO, CH, and anything else through a combustion analysis. In other words, we're going to burn stuff to figure out our answer. To get an empirical formula, we have 4 steps. Before we can use our 4 steps, we need the mass of each of the pieces in the molecule, or the percent by mass of each piece, but in this case, we'll figure out the mass of each of the pieces. This particular hydrocarbon has carbon, hydrogen, and oxygen. If we knew the mass of each element, we could run through our 4 steps and get the empirical formula. Our problem is that this hydrocarbon doesn't look like a C and an H and an O on a paper or the board. It looks like a little drop of liquid. And that drop contains these 3 elements in some whole number ratio. So how do we separate these different pieces from the clear drop? Well, we burn it. We are going to weigh out a sample and put it into a furnace. And then we're going to add an excess of oxygen, which means we don't know how much this is, and we're going to burn it completely. In a complete combustion reaction of a hydrocarbon, you're going to get carbon dioxide, and you're going to get water. And since this is in excess, you're going to get oxygen. If there was other elements besides CHO, you might get chlorine or nitrogen or something like that. As our sample burns in the excess of oxygen, it will fill this with gas, and the products will go through these tubes. Each one of these containers has a chemical that absorbs a particular product. The first one is absorbing water, gaseous water, and the second one is absorbing carbon dioxide. These tubes can be weighed in the beginning and then weighed at the end to figure out the mass of water and the mass of carbon dioxide absorbed. The assumption is all of the carbon ends up here with carbon dioxide, and all the carbon that is in the carbon dioxide came from this compound. Also, all of the hydrogen from the compound goes into the water, and all of the hydrogen in the water came from this compound. If we can figure out the mass of the water through subtraction, then mathematically we can figure out the mass of the hydrogen in the water. If we know the mass of the hydrogen in the water, we know the mass of the hydrogen that came from the chemical. It will be the same. If we can figure out the mass of the carbon dioxide, mathematically we can figure out the mass of the carbon in carbon dioxide, and that came from our compound, and therefore we can figure out the mass of the carbon from the original sample. These will be the same. The mass of the carbon in carbon dioxide is equal to the mass of the carbon in the compound, because that's where it comes from. The mass of the hydrogen in water is equal to the mass of the hydrogen from the compound, because that's where it came from. Don't forget, this is a before and after type situation. All this is after the reaction, all this is before the reaction. I like to think in terms of Lego blocks. If you have something built and you break it apart and rebuild something, you have the exact same components and the exact same number. If we started off with 10 blue Lego blocks, we'd end up with 10 blue Lego blocks. If we started off with 20 red Lego blocks, we'll end up with 20 red Lego blocks. So it's the same. If it's the same number of each, it's the same mass of each, and that's what we're working with. Once we calculate the mass of the carbon from the carbon dioxide, and then we calculate the mass of the hydrogen from the water, we just subtract those two, and if you have CHO minus C and minus H, you end up with the mass of the oxygen. Once we get the mass of each of these pieces, we're done with the first part of the problem. After this, we just run it through the 4 steps to get the empirical formula. So I like to look at this as 2 separate problems. One is all of this that we've been talking about to determine the mass of each of the pieces, and then you kind of start all over again to figure out the empirical formula. By the way, even if you calculated the mass of the oxygen in water and the mass of the oxygen in carbon dioxide to equal to the total mass of oxygen, which will be equal to the total mass of the oxygen on the reactant side, we still don't know where each part came from. So we'll have a number equals to X and Y, and therefore we can't solve for oxygen the same way we solve for hydrogen and carbon. The hydrogen and carbon each go to one single compound, and there's a definite starting amount. Whereas since we have this in excess, we don't have a set starting amount of the oxygen. So here's an example in which they give you 2.225 grams of the unknown hydrocarbon. They need to state that it's carbon, hydrogen, and oxygen. They tell you that it's in an excess of oxygen and burns completely to form carbon dioxide and water. The mass of the water obtained is 1.113 grams, and the mass of the carbon dioxide obtained is 4.076 grams. Let's take this one at a time. We're going to get the mass of the carbon dioxide and determine the mass of the carbon. The mass of the carbon in those compounds will be equal to the mass of the carbon that came from this original sample. So we're going to put 4.076 grams of CO2, and then we're going to multiply it by the percent composition of carbon in carbon dioxide, except we're going to go with the fraction, not the percent. If we did the percent, we multiply by 100 and then immediately need to divide by 100 to figure out the actual mass, and that's redundant. So we're going to have carbon dioxide on top, carbon dioxide on the bottom. We're going for molar mass of carbon dioxide, 44.01 grams per mole. And then we're going to see the amount of carbon in 1 mole of carbon dioxide by mass. There's only one carbon, so it's 12.01 grams per mole of carbon. I did the math and I got 1.112 grams of carbon. I'm just keeping 4 sig figs because 5 and 6 are too much. It won't hurt you. It's just a lot of numbers. And then if you round too much, you end up rounding away from your correct answer. Grams per mole are going to cancel. Carbon dioxide is going to cancel, leaving you grams of carbon, and that is what we're looking for. So I can come back over here and put down 1.112 grams of carbon from that original sample. Now I'm going to get the water and do the same thing. I am going to start with the 1.113 grams of water, and I will multiply it by the fraction. A mole of water weighs 18.02 grams. And in that 1 mole of water, there are 2 moles of hydrogen. This is not because it's diatomic, it's because within the compound, there's 2 of them. And again, the grams per mole will cancel, the water will cancel, leaving you grams of hydrogen, and that is what we're looking for, grams hydrogen. Doing the math, I end up with 0.1247 grams of hydrogen, and that also came from the compound, so 0.1247 grams of H. Now I kind of cleaned this up a little bit because we needed those 2 masses from the carbon dioxide and the water. If we have CHO and we subtract out the C and subtract out the H, we end up the mass of the oxygen. And to end up with 0.9883. That is the end of the first part of the problem. And now we want to do is expand this out a little bit and then run through our 4 steps. Our first step is convert percent to mass. Well, we already have masses here, and therefore we need to convert the mass to moles using atomic masses, not diatomic molecules. Once we get a mole ratio, we want to reduce it by dividing by the smallest one. And then if there's a fraction remaining, we will multiply by the denominator. So we will divide each by the atomic mass, like so. Notice that oxygen and hydrogen are both from our diatomic molecule list. However, within the compound, they're not diatomic molecules because that only counts when you're by themselves and uncharged. Within a compound is definitely not by yourself. My answers to the right are the mole ratios that would go as subscripts. However, I don't think this would be a good looking subscript right here. These are definitely not whole number ratios. So the next step in our 4 steps would be the third one, a must step. People often try to round at this point and they mess up. So please do the third step, and that is divide each by the smallest one. That ensures that one of the answers is 1 and everything else is greater than 1. After doing our third step in blue, I have a 1.5 to 2.0 to 1.0 ratio. And the 1.5 can be thought of as 1 1/2. The last step states that if a fraction remains, and there's clearly a fraction, we're not going to round 1.49 down to 1. These fractions would be simple fractions like 1/4, 1/3, 1/2, 2/3, simple like that. You're not going to get 7/8 or 13/16. So the fourth step says if a fraction remains, multiply by the denominator, which is 2. Don't forget to multiply the whole number and the fraction by the denominator because a lot of times we get the wrong answer. But if you multiply one of these by 2, you have to multiply each of them by 2 in order to retain the same ratio. Now you're almost done. All we have to do is to apply these numbers as subscripts. So we end up with C3H4O2, and that is my empirical formula for the hydrocarbon that we burned. Remember, all of the carbon went to carbon dioxide, and that's how we got the mass of the carbon. All of the hydrogen went to water, and that is how we got the mass of the hydrogen. And the oxygen we just got from subtraction, because if you know the whole thing and you know 2 of the parts, then you can find the third part by subtraction. I hope this video helped. See you tomorrow in class.